Alright, so I got some good news and I have some bad news. The first piece of good news is that this is the final preparatory lesson before I teach the framework. That's right. The next lesson, lesson 4 of the intermediate series, is going to be on the framework. But this lesson, I'm still covering some topics that I want you guys to know before I actually go to the framework. Last lesson for the framework, and I'm going to keep this one short, so you're not going to have to, sit through 3 hours of me preparing you for learning the framework. This one will be probably it'll probably be a little bit more than an hour long, but I'm going to cover 4 independent topics, so you're really getting 4 15-minute lessons here. Think about it that way. 4 quick 15-minute lessons. You can watch them. We can watch a couple of lessons, then pause it or whatever, or stop it and come back later. That's that. And now for the bad news. The bad news is that because I'm covering these things rather quickly, I'm not going to have time to go very in-depth or do something that's practical. So I'm not going to give you like a practical game-related type problem for these, or really much practical coding at all. It's just going to be a quick introduction of some language features that will come up in the framework. So, yeah. And some of these things will be useful practically when you're coding yourself. Some of them not so useful, but they're all stuff that you should know. So just watch the videos. Don't worry if you don't feel confident about being able to use these things yourself. That's not the point. The point is just to get a little bit of familiarity with these topics. And the stuff that is useful, I will be using a lot, and the stuff that's not useful, you don't have to be an expert on. Just so that you kind of have an idea of what this shit is, and if you get that, then that is mission accomplished. Now, the 4 topics that we're going to be doing: function pointers, references, constant correctness, and this stuff. So I'll be covering these 4 different things, and I'll probably put links in the description that will give you the times at which these topics start, so you can jump between them. So it makes it easy if you want to, watch a couple and then take a break or whatever. Alright, so let's get it on. Alright, so function pointers. Function pointers are pointers to functions. They allow you to call a function by a pointer rather than calling it by its name. Now, what the fuck does that actually mean? Well, I got this console application set up here. If you want to follow along, you know the drill. You can set this up yourself, or you can just watch me. I don't care. Function pointers. Well, we know normal pointers, right? That we've been using up until now. They point to data or variables, or somewhere inside of an array. They point to some location in memory that holds some data. And basically what a pointer is it's a variable that holds the address of some data. Normal variables hold some values that mean something in our program, and pointers hold addresses to those normal variables, or to just some data in a block of allocated data, whatever. That is pointers. So, pointers hold addresses. They point to data at some address. Now, functions. What are functions? They are routines. They are a sequence of instructions that exist in memory. Instructions are just like any other kind of data. They exist in memory. The CPU has something called an instruction pointer, which tells it where in memory the next instruction is, and it goes and it fetches that instruction, and it decodes it, and it determines what it should do. Should it load some data from memory into a register? Should it add two registers together? Should it store a register into memory? It loads an instruction, it does what the instruction tells it to do, and then it loads the next instruction, and it keeps on going. Those are instructions, and they sit in memory. And a big sequence of them sitting in memory is generally called a function. A function can be jumped to from any other point in code, and it returns back to where it came from. Now these functions, if you look at them, the first instruction in a function would be the beginning of the function, and it would have an address. So just like an address of some data, you can also store the address of the first instruction in a function. And that, my friends, is a function pointer. So let's make a function pointer. To make a function pointer, we need a function. So let's create a function. We'll call this function int funky. We'll call this one the funky one. And it will take two parameters, int a and int b. And it will return a plus b. So it's just an adding function. We could call it add, but I prefer the name funky one. And let's do some crapola. We'll go int my a, int my b. We're going to give these ones numbers. We'll give this one a 2 and a 3. And then we'll go printf. Wait. Well, let's just do this for now. Printf a %d b and %d. I'm gonna put a new line in here and another new line here, and we'll just say result, and it's a big %d. That sounds good to me. And we'll get another backslash in there, and then we want a, b, and the return value of funky one called with a, oh wait, my a. Sorry, my bad. My a, my b, and funky one called with my a and my b. Okay, so here is very simple, just calling a function and displaying the result. We shouldn't have any problems. Alright, I gotta start without debugging. Alright, so a and b, and the result is 5. 2 plus 3 is 5. So far, so good. Now we get to the pointer, function pointer thing that I was talking about. How to declare a function pointer. Well, first you have to give the type, the return type of the function, which is int. Then you give the name. Actually, I forget how to declare a function pointer. I'm just going to fake it. My func. Wait. P-func. There we go. Now you got to put a star in here, but I'm not sure if you put it before or after. I think it's after. And then you have to give the parameters that the function pointer takes. I think the star is in the wrong place. I'm going to put the star here and see if all those nasty underlines go away. No, they don't. Alright. So int pfunc is... we'll just declare that. It did. Okay, look good. And now we can... That's how you declare a pointer to a function that takes two ints and returns an int. Remember, normal pointers have to be a pointer to an int or a pointer to a float. It has to be a pointer. You have to declare the type that it points to. And with function pointers, you have to declare the type of function that it points to, meaning you have to declare what the parameters are and what the return value is. So this pfunc points to a function that takes two ints and returns 1. Now we can say pfunc is equal to funky1. The name of a function without the brackets after it is, or without the parentheses, is the address of that function. Just as the name of an array, a statically declared array, just the name by itself is the address of the first element in that array. So now I can call my function. Let me just copy this. I can call my function by pointer. So instead of going funky1, I can go pfunc, and I'll just go here, pointer result. So now I'm calling pfunc, and pfunc is pointing to funky1. Right. Now I can start debugging. No, I meant start without debugging. And here we have pointer result is the same as the result because it's calling the same function. It's just we're calling it via the pointer this time. So let's just test this out. We'll go, wait. I'm going to be sneaky. Funky2. Well, wait, I'll do that later. First thing I want to tell you guys is what happens if we change funky1? What happens if we make the second parameter in funky1 is going to be a float? Okay? What's going to happen? Well, we're going to get a warning here because we're trying to pass an int to a function that takes a float, so it has to convert it. But it won't be an error. But what else will happen? So yeah, we get a warning, conversion from float to int. But here, we get an error. Cannot convert from int, don't worry about this, basically int function pointer int float, which is funky1, to int function pointer int int. So you cannot make a pointer from one type of function point to a different one. The compiler will not let you do that shit unless you force it. Unless you pinch its nose closed and you say, swallow, bitch. But generally, that doesn't work. So you just make sure that your function pointer type matches your function type. Okay. So I didn't want to do that, but I did it anyways. That's what you get when you're talking and typing at the same time. Okay, so now we got funky1 and funky2, and just as a quick demonstration here, I'm going to call this function with pfunc. Here. So I'm going to do the same thing. This is the exact same line, but what I'm going to do is, no, where's my delete key? There we go. Here pfunc is going to be set to funky1, and here pfunc is equal to funky2. So same pointer, but before I call it a second time, I make it point to a different function. So if function pointers are not bunk, then we should be able to get a different result the second time we call this. Let's do it. So the first result was 5, the second was -1, which is what we expect given our two different functions. So that's function pointers. That's pretty much all I wanted to say about them. Function pointers aren't something that you're going to want to use yourself. Well, there was one more thing I wanted to do, and that is you can make a function that takes a function pointer. So my func, and it'll take int a, int b, and it will take a pointer to a function. And wait. Yes. And then you can do something like this. You can just I'll copy that there, I'll put that there. It's so good. And now, I can keep... fuck it. I'll get rid of that too. Get rid of all this shit. And now I can do something like call my func. And I'll give it a 5 and a 3. And I will call it with funky1. And then I'll call my func again with 5 and 3. And I'm going to call it with funky2. So I can... Wait. That's not right. I can call a function and pass it a pointer to another function. And depending on the function that I pass to it, I can change the behavior of the function I'm calling. Alright, my A might be... Yeah, okay. My bad. A, B, A, B. There. Are you happy now? No, you are not happy. My func must return a value. Oh, fuck. My func is a void function. Dude, I totally typed void. You just listened wrong. Okay. And again, we get a different result both times because we called my func with a different function address here. So you can do shit like that. But you probably won't be doing anything like this. You probably won't be making functions that take pointers to other functions or making function pointers because there's no real reason why you have to do this in your programs, and it's kind of messy. And later on in C++, we'll be getting to dynamic binding, which can let us do the same sort of stuff that you can do with function pointers, but it lets you do it a lot sexier. So then, why did I teach you function pointers in the first place if I'm telling you you probably shouldn't use them? Well, the fact of the matter is, if you're going to use some APIs or some libraries, you're going to need to create functions and pass those functions to functions in the API or in the library. Those are called callback functions. Normally, if you have an API, an application programming interface, or a library, you have a bunch of functions that you call and they do shit for you. But sometimes a library actually calls one of your functions. So you have to pass that function to the library as a function pointer. And when an API or a library calls one of your functions, it's called a callback function. Because normally you call forward, you call the library functions. And the library functions calling your functions is it's not a usual situation, so we call it a callback function. Now, last thing I'm going to show you before I end this section on function pointers is not YouTube. That's not what I was going to show you. Disregard that. What I was going to show you is qsort. Qsort. This is a function that is part of the standard C library, and it will sort an array of data elements for you very quickly. Now, the neat thing about qsort is it will sort basically any kind of data you want it to sort. And that's interesting because think about it. When the people who wrote this function, to be able to sort data, you have to be able to compare two things and determine which one should go before the other. Now, it's easy to compare an integer or a floating point value. But what about a complicated class that has a bunch of different things that have to be factored in to determine which goes before the other? These user-defined data types that didn't exist when this qsort function was written. How do you compare data that doesn't even exist yet when you're writing a function? Now, the way you do it is you write an incomplete function. You write a function that sorts data by comparing it, but the comparing function you leave unimplemented, and what you do is you take it as a parameter. So qsort, it accepts a pointer to a comparator function, and that comparator function will compare two values in the array, two elements, and determine which one goes before the other, or whether they have the same value. So when you are calling qsort, you have to provide a comparison function. And if you didn't have function pointers, that would be, you couldn't have a qsort, a general qsort like this, a general sorting function. You'd have to think of you would have to anticipate every kind of data that people would want to sort and write a different function for every different kind of data. But with the function pointers, you can write a generic function, and all you have to do is change the comparison function that you pass, and you have to also tell it the size of the elements and so forth. But yeah, so this is one application of function pointers. And the other application that I'll show you later is in the framework. There is something in the Windows API that requires function pointers. But yeah, okay, so that's function pointers. And if you want a challenge, like a kind of homework deal, why don't you create a structure, like for example a structure with student name and student number or something like that, and then create an array of elements of those structures and use qsort to sort them. So that's a little challenge for you guys if you want to try it. Try to figure out how to use qsort. There's example code here, and there's an explanation here, so it shouldn't be that hard. Anyways, I only wanted to do 15 minutes on function pointers, so I'm already 4 minutes over. So that's function pointers, and that's this section finished. Alright, so the next topic is references. What are references? Well, references are, they're actually a lot like pointers. So what are pointers? Oh, you cannot be seriously asking that question. Grr! I want to stab myself with a fork in the eye. But I'm going to tell you what pointers are again anyways, very quickly, in like 30 seconds. Pointers are like this. You have a variable, and you can access that variable indirectly via a pointer. A pointer can point to any variable or any part of memory that you want. So look at this little bit of code here, which I fucked up because I forgot to put my goddamn new lines in there. I always forget the new lines. That's an M. My line breaks. There we go. Okay, let's do this. Let's do it. So we print out myInt, and we get a 5. And then we change pint, or we change the thing that pint is pointing to, and then we print out myInt again, and we get 69. So we could change myInt without actually directly using the myInt variable. We accessed it via pint, right? This gets our address. We get the address of myInt. We store the address in the pointer, and then we use the dereferencing operator to access the memory that the pointer is pointing to access the address that it stores. All right, so that's pointers. Now let's do this with references. So let's see here. How do I do this? Well, first I got to get rid of my pointer. Fuck off. And we're going to make a reference. So how do we make a reference? We go int, we got to give the type of reference. And then we use an ampersand, because that's how we roll with references. And then we go, we'll call it int ref, is equal to myInt. And here we'll go int ref is equal to 69. So this may look strange to you if you're used to only pointers, but if we try to build it, success. So let's check it out. And the exact same thing happens because references are like pointers. References are like pointers except for one or two small little details. First of all, the syntax is different, obviously. If you're declaring a pointer, you use a star. If you're declaring a reference, you use an ampersand. When you're making a pointer point to something, you get the address of that thing with the address of operator. If you're making a reference point to something, you can just say equals the something, and that will make it point to it. Now here's the big difference between pointers and references. Pointers, you can make them point to one thing, right? Like for example, let's say I've got int myInt, and I've got int anal beads equal to, I used that one already, equal to 411. And I go pint is equal to myInt, and blah 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 blah. I'm gonna get rid of this thing here. No, I'm gonna leave it. Now I'm gonna comment it out. There we go. So I can say anal beads is equal to 411. Yes. And then I can say pint is equal to the address of myInt, and then I can do all this crazy shit. Here's the problem with talking and coding. It doesn't work for me. And I'm just going to show this. I'm going to comment all this shit out. Comment to you, you go to hell. You're fine. And then I can do this. pint is equal to address of anal beads. So I can make it point to one thing. Later on, I can make it point to something else. That's fine. Nothing wrong with that. I can point wherever the fuck I want. But let me comment this out. Let's go to our reference here. So I can make my reference point to myInt, or refer to myInt, however the fuck you want to say it. Now let's make my reference point to anal beads. I could do something like this. Well, that works. Except it fucking doesn't work. Let me show you why it doesn't work, okay? So, one second. I'm gonna set something up here. Alright, so here's the deal. First I create these two variables. I call them myInt, and I call the second one anal beads. I print out their values. Then I create a reference. I make the reference point to myInt. I change the value of the reference by shoving 42 into the thing that it refers to. And then I print out the variables again and see what happens after this. Then, well, to make int ref point to myInt, I just did this assignment. So to make int ref point to anal beads, I should be able to do this assignment again, shouldn't I? So I'll assign int ref to refer to anal beads. Then I will move 99 into the thing that int ref refers to. And then I'll print out the variables again. And this should all work exactly the way I want it. We should have 5, 411, 42, 411, and 42, 99, right? That's what we're predicting. And holy shit, that's not what happened, is it? Not at all. Plus, I fucking forgot to put the fucking and wait a second. Okay, that's much better. Now I got this all sorted out. So 5, 42, 99, and anal beads doesn't change once. So why the hell is that? Well, let me show you what happens if I comment this thing out here. So now we're not moving 99 into the thing that int ref is referring to. Now what do we get? Now we get 5, 42, and 411. So here, what I thought I was doing was I thought I was assigning int ref to refer to anal beads. But what I was really doing was I was moving the value of anal beads into the thing that intref refers to, which is myInt. And the reason is because with a reference, you can only make it refer to something or point to something once when you create it. And once you make it point to something, it'll never point to anything else. It is a highly monogamous pointer, whereas normal pointers are rather promiscuous. So that's the big difference between references and pointers, is that they, once you make them refer to something, they refer to that thing forever. And the other thing is, of course, you don't have to put a star in front of it to refer to the thing that it points to. Once it's pointing to something, that's it. It just acts like that variable. So you can just use it like you would use a normal variable. You don't have to put a pointer in front of it, like this. And you can't do something like an index. That is also not acceptable with a reference. You cannot index a reference. You cannot dereference a reference because it's already it's permanently dereferenced. And you can't increment, you can't do anything with it except for use it like you would use a normal variable. So that's the thing. Declaring references, you use the ampersand, you make it, when you initialize it, you make it refer to something. And then after that, it just acts like a normal variable. But it's not a normal variable, it's a reference. Okay, now let's do something a little different. So we've got myInt and we got anal beads here. We'll print them out. Then we'll call swap. And you guys should be familiar with swap from my lesson where I introduce pointers. So we'll call swap. Wait, that's not A and B, it's myInt and anal beads. Build that. Yeah, it succeeded. And so we should get 5411 and then 4115 because we swapped them. Swap is just like this. So go. And indeed we have swapped our variables. So how do you think we will do this with references? If you want, you can stop the video and try making this swap function with references. But I'm going to do it right now. So if we're going to make this function with references, again we use the ampersands in the parameter declarations here. That's the first difference. The second difference is because they're references, we don't use the dereferencing operator. We just treat them like normal variables. And the last difference is we don't pass addresses. When we pass a value by reference, we can just type the variable like this, and it will be the A and B will take a reference to these myInt and anal beads. So when we're passing the values, it's just like passing by value instead of passing by pointer. So it looks like we're passing by value from this side, but we're actually passing references to these variables. And if we build it, same effect, but different. So I mean, you could argue that this actually looks prettier. You don't have all those nasty ampersands here and stars here. But whatevs, it's not a big deal. That is references, and that's pretty much all there is to them. Mostly, for now, anyways. We'll be using references a lot because, like everything else in C and C++, the more you can restrict things, the better. So references, they restrict where things can point. They can only point to one thing. They're locked in. So they're safer. And they're more convenient, I guess, from the viewpoint of syntax. There's other reasons why you use references. Especially if you're going to be overloading operators, which you can do and we'll do later. You need to use references, but that's a story for another day. So that was references. Ta-ta. So, const correctness. What is const correctness? Well, in a nutshell, const correctness is the correct usage of the modifier const with your variables and functions. I'm going to try to go over different usages of the const keyword, and I'm going to try to explain why it's good to use this properly. And that's kind of hard. I'm also going to try to do it in less than 20 minutes, so yeah, good luck with that. First of all, let's recap. I've used const before, and I've used it to basically declare variables. Look at this one here. We've got const int answer, which as we all know is 42. We can use const like this to kind of declare, constants that you guys are probably familiar with, like universal constants of physics or something like that. Numbers that don't change, right? That's the essence of const. And then if I were to try to do something like assign the value 5 to the answer, clearly wrong. We get an error here. The compiler says, what you getting all up in my grill for? It tells you answer you cannot assign to a variable that is const, right? It's stuck at 42, whether you like it or not. So that's the simplest usage of the const keyword. But the rabbit hole gets much deeper, my friends. Take a look at this function here. This function returns a and b, or the sum of a and b. So it's basically just an adding function. What happens if, well, let's try this out for a second here. We're going to go printf. We'll go %d \n, and we're going to print out the return value of func. Wait, I need variables because these are references, so we need variables to refer to. So let's go int. We'll just do a here too. We'll go a is equal to 5, int b is equal to -2, and we'll go func a and b. All right. Build solution. Good times, good times. Start without debugging. And the answer is 3, right? 5 plus -2 is 3. So far, so good. So what the hell? That doesn't make any sense. What's the point of this const here? Well, when you put const in front of a reference or in front of a pointer, you're basically you're making a promise, and you're promising that whatever variables are passed to this function by reference or by pointer, you will not change their values over the course of the function. You're gonna look, but you're not gonna touch. That's basically the promise that you're making. And if you try to break that promise, for example, if you try to go here and you say b is equal to b times 2, and then return a plus b, build solution, you're going to get a failure. B you cannot assign to a variable that is const. Same deal as before. So this is putting a restriction on what this function can do with these variables. And that's a good thing, because if the function is just supposed to add the variables together and give you the result, the function should not be changing those variable values, and that would be unexpected. And by putting const in front of these, you're making sure that you're not going to fuck something up down the road. I mean, of course, looking at this function, you're like, I'm never going to fuck this up. But when your function is like, I don't know, like 200 lines of code, yeah, you might fuck something up. It's conceivable that you will fuck up. And doing shit like this will lower the chances of you fucking up. So that's one thing. And this kind of usage of const we see all the time if we look, well, let's look at printf. First thing it takes is a constant pointer, a constant character pointer. And what that is saying is that this string here, it's not going to try to change it. It's just going to look at it and use it as a format string. It's not going to try to change this. So that's good to know, because some strings you shouldn't be changing. Because it's bad, okay? So if you look in the standard library, there's tons of functions that take constant pointers. They do it wherever they can, whenever they're not going to change anything. Let's look at string.h. And if we just look at anything like string length, which gets the length of a string, it takes a constant pointer. What else do we got? String copy takes a normal pointer to the destination and a constant character pointer to the source. And that's because it's only looking at the source, but for the destination it actually has to change it. It's copying, so it has to change the values of the destination. So it keeps the source constant and it makes the destination just normal pointer. So that's one way of using const, to basically restrict pointers and references so that you don't change their values. Now the other reason, or the other way of using const, is in functions. You can have a member function, a method that is constant, and you declare it over here. After the parameter list, you go const. Now what does that mean? Well, this is also a promise. And this promise states that this method will not change the state of this the object that's based on this class. It doesn't change the object state. So it's not going to change any of the data members of this class. So let's see how this works. I'm going to create a thing. I'll go thing, my thing. And I don't know, I'm going to pause the video. Alright, so here we create a thing object. We call it my thing. And we print out the value of our thing. Then we increment our thing. And then we print out the value of our thing again. So we should get a 0 and then get a 1. And we get 0 and 1. So far, so good. Now, let's do something a little different. Let's create a constant thing reference. We'll call it thing ref. And we'll set it to refer to my thing. Alright. Build that. So far so good. So we can create a reference that refers to our thing object. Now we're going to comment this out. Comment that. And we're going to use the reference here to get the value of my thing, and we'll print it out. And that works. 0. Okay, now we'll use the reference here to increment it, and we'll use the reference here to get the value again. Uncomment that. Build it. And error. No, we don't want to run. Error. Thing increment cannot convert this pointer from constant thing to thing, and conversion loses qualifiers. So, reading this error message, you'll be like, what the fuck? This is the most cryptic error message ever. So let me break it down for you. Because thing is, our thing reference here is constant, we're not allowed to change thing. So we're not allowed to change any of its variables. And when we have a constant reference or a constant object or whatever, that means we aren't allowed to call any we're not allowed to call any methods that aren't constant. So for thing, we're only allowed to call getValue because it's constant. It's promising that it will never change the value. Whereas increment doesn't promise shit, so we're not allowed to call increment. That's not cool. not with our thing ref. If we call it with my thing, which is not constant, then it's cool. It's like, the compiler's like, yeah, that's cool, you can do that. But try to call it with thing ref, which is a constant reference, and the compiler's like, nah, fuck no, that's not happening. We can also make the thing object itself const. Let's do that. Thing, my thing, my thing. Build. And the same deal. Right? You can't call increment. If you forget about incrementing it, if you just say, I just want to get the value, then that's fine. That's no problem. Everything is good. So how do we solve this problem? Well, fucker. You stay there. Okay. I'll just get rid of this reference here. You might think, well, we could like bamboozle the compiler. We could be all sneaky like, and we could just say, yeah, this is a constant method. Sure it is, but that's not cool either. Value cannot be modified because it is being accessed through a const object. So if we declare a method as const, it is not allowed to change any of these variables inside of the method. So the compiler is a little too smart for that. So the moral of this story is, if you want to change the state of a variable, you have to have a non-constant object or non-constant reference. Lose the const and you're fine. Now you might say, why would I ever want to do this shit? I mean, why would I want to restrict myself? And again, it's the same thing. The more restrictions you place, the more things that, if it's not supposed to change, you should declare it as constant. That's just the way it is, because that will lock things down, and it'll minimize the amount of things that can go wrong when you fuck shit up. So if a method is just calculating and returning some values, you can make it constant, and that way, if you have a constant reference to the object, you'll still be able to use that method. So you should declare as many methods as you can as constant methods. Similarly, when you have functions or methods that take parameters, you should declare as many of the parameters as you can as constant parameters. That is constant correctness. You only expose things to change which absolutely should be changed. If things shouldn't be changed, declare it as constant. If there's no reason to change them, declare it as constant. That's the way to roll. That's how the cool kids program. And that, my friends, is const correctness. And I'll be, as I code, when we actually get onto real big-ass projects, I'm going to try to remember to be const correct as much as possible. But if I slip up, if I write a function and I should have made it const but I didn't, or I should have made a pointer or a reference const but I made it just a normal one, you guys can jump on me. You can let me know, holler at me in the comments. But hopefully that won't happen. I'll try to keep it in mind. Because I mean, even I forget to make a method const when I could have. Plenty of times it slips my mind. So, but I'm going to try to keep on it for you guys. Do it for the kids. So that's const correctness. I'm sure it's not the most exciting thing you've ever heard, but it's one of those things that separates a good programmer from a total piece of dicks. Wait, that doesn't make sense. A total bag of dicks. There you go. All right. So stay tuned for the next topic in my mini topic bonanza. Scope and static. No, jackass. It's not this. So what is scope, first of all? That's not it either. What is your fucking problem? Okay, I got it. Gotcha. Understood, bro. So scope keeps your breath fresh, but what else can it do for you? Well, this is something that's usually taught a lot earlier in any kind of program of teaching programming. Yeah, that sounded stupid. This is a topic that's usually covered earlier, but I didn't feel like covering it because it's kind of bullshit. But I should cover it sometime, so let's cover it now. So scope is the place where variables live and crap. So for example, let's say we have a function. We'll call it func. And inside the function, I could declare an int. We'll call it int a. And that int a lives from wherever I declared it until the end of the function. So that is the scope of the variable int a. Now let's say I make another variable, int b. Well, b is the scope of b. If it's inside of this if statement, then it will live from here to the end of this if statement. That's its scope. So that seems very common. I mean, if you guys have been following so far, you probably already have figured this shit out. Now here's one thing, another thing you probably know. If I say int a and then right after that I say int a again, the compiler's going to say, what the fuck, brah? Because you're trying to declare two different variables with the same name, and it's like, how am I going to tell this shit apart? So the compiler says, nah, and you got to fix that shit. So you can't declare two variables with the same name in the same scope. That is impossible. But you could declare an int a over here, and that would be fine because this function and this function, they're separate. So these are different scopes. You can have two variables with the same names in different scopes, and they're just completely different variables. You change this a that has absolutely no fucking effect on this a over here. They're completely separate. They only have the coincidence of having the same name. Now, what happens is if I have some variable a in my main function and I want it to be to use that variable in my func function, I have to pass it to the func function. Otherwise, the func function won't be able to access this because they're in different scopes. So I would have to put like some parameter here. I could go int I don't know, p for parameter, and then in here I would go func, and then I'd pass it a, and then the value of a would be passed to func, and it would be loaded into the p variable, whose scope would be from the beginning of func to the end. And yeah, that is how I could use this value here inside of my func function. I have to pass it to the function. Now, there is another way of being able to share a variable between two different functions. And that is if you declare it globally. So just like func and main, these are all declared inside of the global scope at the very, at the very root level of your CPP file. And I could declare an int gvar here for global variable. And if I did that, I could access gvar from here, and I could also access gvar from here, and they would change this variable, because the scope of gvar is basically the entire CPP file. I'll call it balls.cpp. Yeah. So its scope is basically this entire CPP file, and its lifetime is from when the program starts until when the program ends. So it lives for as long as the program lives. That's what a global variable is and what it does. It can be accessed from anywhere, and it lives as long as the program lives. Now you might be thinking, wow, this is sweet. Now I don't have to pass all these parameters and everything can access this. It'll be so convenient. No, fuck no. This will fuck your programs up because now everything can access. If you made all your variables global, which you could do, it's perfectly possible and fine. And if you did that, basically everything can access everything else. And when something fucks up, you aren't going to know where it's fucking up because every function has the possibility of fucking up every variable. So when you're trying to debug that shit, that becomes really fucking hard. And that's why we like to keep things as local as possible. Keep things as local as you can. And generally, we can get away with very few global variables if you don't completely suck at programming. So, global variables and stuff and other stuff. What else do I want to talk about? Well, one thing about scope that you may or may not have realized is there's a kind of an effect if you declare variables in different overlapping scopes. Like I've color-coded the scopes in these functions. Here's a scope here. There's a larger scope here that contains this scope. There's even a larger scope here that contains these scopes. And then there's the global scope, which contains everything. Now, if I declare a variable int a here, and I declare another variable int a over here, you see that there's going to be some kind of collision here because I could access a from my func. Now, how does the compiler determine when I say, for example, a equals 5, is it going to put it in this int a or is it going to put it in this one? And the answer is, it puts it in the most local scope possible. So if I say a is equal to 5, it thinks I'm talking about this a, and it ignores this a completely. And I could even create a third a in this scope. I could go int a is equal to 6, and it would move 6 into this a. It would leave this a alone. It would leave this a alone. So you see, whenever you create a new scope level with a code block, these curly braces, and if you put a variable name that has the same name as a variable in a higher scope level or a more global scope level, then the local variable will eclipse all of the higher ones, and that will be the only one you can access inside that scope. So, yeah. One last thing that I wanted to mention about scope and shit before I show you some coding examples is if I have a parameter here. Let's say I have a parameter that goes inside here, inside of the func, and that parameter is int p. I don't put semicolon after that because it's a parameter list. That p will actually exist within this function scope. So I can't go then int p here. That would not be kosher. But I could go int p here because this scope is different than this scope. So parameters, their scope is for the entire function. I'm pretty sure that's true. I haven't actually checked it. As a rule of thumb, you don't want to use this scope eclipsing thing. You don't want to do it too often because you can get fucked up. You can trick yourself. You can think you're accessing one variable when you're actually accessing a different one. So especially when you're debugging, because when you're debugging, you'll see all these variables. You'll see, like, if you have A here and A, if this was a P, and you had the P here, and you had a P here, and you had a P here, you'd see all these P's in your watch window, and you wouldn't know which one is which. And you'd be like, fuck. So, in general, try to keep your names so that they don't eclipse each other. Sometimes, you don't want to, you can't avoid it, or because of naming convenience, you do it, but in general you should avoid it. So yeah, that's what I wanted to say about scope. Now let's have a demonstration, shall we? Alright, so for those of you who enjoy a challenge or are just plain masochists, why don't you try and predict what the output is going to be for this code here? Have you done your prediction? Alright. Well, the first thing you're going to notice is that it won't build properly. Why? Because of that thing I told you about like 2 minutes ago, which is that we have A here, and then we try to do A here. But the parameters and the function scope is the same scope, so you get a redefinition. So you have to lose one or the other. So we're going to lose this definition here. So that's one of our A's down. Now let's build it again, and we succeed. So let's run it and see if your prediction is correct. So we got 1, 5, 3, 6, 4. Is that your number, gentlemen? Is that your card? So why do we get this? Well, let's run through the program and analyze this for a second. So the first printf we will reach is here at the beginning of the main function, and at the beginning of the main function we have not declared any A variables. So that means that A refers to the global A, which we have up here. The global A, which can be used throughout the entire function, or throughout the entire CPP file, main.cpp. So the first one is going to be the global A, which is 1. Then we create a new A in the main scope, and we set it to 4. Then we enter this code block. And yes, you can have a code block without having any kind of control statement. That's possible. And even sometimes it's even useful. But now it's just for shits and giggles. So we create another A, and we set it to 5, and then we print F again from A, which is this A, 5. Then we call func with A plus 1. And since A is 5, A plus 1 is 6. So this A is 6, and the A which is in the func scope is 6. Then we enter this if statement. We create another A, we set it to 3, and we print it out. So we get a 3 here. Right? Keeping track. 1, 5, 3. Then we leave this if statement. This A becomes dead. Dead to us. You are dead to me, A. And we print out A, which is this A, which was 5 plus 1, 6. Then we return from our func. We leave this block, and because we leave it, this A dies. So now our the A that is currently in scope is this 4, and we call printf, and we get a 4. So that just proves that shit that I told you was not actually bullshit. It was true. What else do I want to say? I guess I want to teach you one more thing. So we're going to create another function here. Wait a second. Actually, I'll just do this on camera. This one's going to go a little longer than I wanted to, but whatever. Fuck you, bro. I want to add a new item. And we'll call this one stuff. That's an incredibly pithy name, I know. And we'll also do a # include on this mother. # include stdio.h. and we're going to create a function void, and we'll call it static test. We'll call it stest, and it'll be void. Now here's the deal. If I wanted to, I could access this variable, this global variable, from within any function in this CPP file. But if I had a different CPP file and I wanted to access A, let's say I wanted to do I still have it? Yes, I do. I wanted to print it out from stest. Now I could build this, but it's going to say A is an undeclared identifier. A does not exist in this CPP file. It exists in this one. But it's global. So we could do something so that it could be accessed from another CPP file. And how you do that is you go extern int A. And what that says is that there is a global int in a different CPP file, in one of the other CPP files. So remember that. And when it comes time that these are all linked together, the linker will search for the external global A, and it will link it to the A in this function here. So what that means is that I could do something like, for example, I could create another function. I could call it void set A. And here I'll just do A is equal to 69. And what that will do is, because this one has no other local A, it will set this A to 69. And in this, in main.cpp, first I have to give a prototype for my function here. So I'll get my stest function, and I'll go void stest like this. This prototype will just let the compiler know that this function exists. And then I can call, at the end of the program here, I'll call stest. I'll print out the global A. Then I'll call set A to change A. And then I'll call stest to print it out again. And if I build, so here we get a 1 and then 69 because we changed it. So this function changed this global variable, and then this function accessed this global variable. That is how you can export global variables to other what we call these things is, every CPP file is called a translation unit, if you want to be technical. So you can export these global symbols, global variables into other translation units and use them in there. So why am I telling you this? Is it because I want you to do this? No, I do not want you to do this. This is a bad idea. I'm telling you this because there is actually a way that you can create a global variable, but you can prevent other modules from importing it. And how you do this is you say it is static. And that's where the static part of this tutorial comes in from. If I call this static int A1, and then I try to compile this mother, it's going to fail, and it's going to say error link unresolved external symbol. So we told it there's this external integer called A somewhere in one of the CPP files, but when it tried to find it at the link step, it couldn't find it because by making it static, that hides it from any other modules. So I can create a global variable that can only be accessed from this module, and I can prevent the other modules from, touching my private parts, which is always a good thing in programming. So that's how you make a global variable, and that's how you make a static global variable. Now the static modifier can be used in a lot of different places. It can be used in class functions, member functions. It can be used in the variables of a class. It can be used in variables declared inside of a function. and it can be used in global variables, and probably some other places that I'm forgetting. But well, we won't get into those other uses. We'll just talk about this one, because this use is the one that actually comes up in the framework. I think. I could be wrong. No, I think that's where it comes up in. So I just wanted to explain that and explain global variables in general, because I haven't actually talked about them. And also explain a little bit about how scope works and how about the way that variables with the same name eclipse each other. So a lot of it is probably stuff that you guys have figured out already by yourself, but I just thought I'd go over it. Now, like I said, global variables are a bad thing. You want to keep things local. You want to keep things so that they're not, all your functions can't touch all your goodies. You want to keep your peas away from your carrots, just like in those TV dinners. You want those separate little trays. You don't want any mixing. And the thing is, though, one second, I'll be right back. Alright, so like I was saying, the thing is in our programs here that we've been making, we haven't been making any actual global variables, but what we have been doing is we've been making all of our variables inside the game object, right? And then we made all our functions in the game object. And the end result is that all the functions can access basically all the variables. And so we get the same, we basically get something that's almost the same as having all of our variables as global, because all the functions we make can access all the variables that we make. So it's not global, but it's almost as bad. And that is why from now on we're going to be making more and more classes and stuff like that. And the classes are going to have private data, right? And because of that, the game object won't be able to access all the data. It'll only be able to access the data or the methods that it'll need. And also, since we'll have the data and the code grouped into separate objects, those objects can't access each other's data. They can only access the stuff that we let them access. So up until now, we haven't been programming like real programmers. We've been programming like, newbie type programmers. But hey, it's the way you got to start out. But I just want to let you guys know that up until now, we've kind of been making all of our variables global, and it's bad, and you should feel a little ashamed, but don't worry, we'll fix that. We will be fixing that. So, that is scope and static variables. And yeah, that's all I got to say about that. Make sure you brush 3 times daily. Circular motions. Okay, so that is that's the preparatory lessons all finished. So as I promised, next lesson we're going to be starting on the framework. And well, first I'd just like to say that again, if you don't think you've 100%, if you don't understand these 4 topics 100%, that's fine. That's perfectly fine. Don't worry about it. As long as you have a general idea of what these things sort of kind of are, then that's perfect. That's fine by me. Don't worry about watching this shit over. Just go right to the next lesson. Unless I haven't made it yet, in which case, whatever. Go outside, have a pizza pop. Yeah, so the next lesson, again, it's not going to be lots of hands-on coding, because obviously I'm going to be explaining shit that's already been coded. And I'm also going to have to explain a lot of the background, like the way the system actually works as far as video hardware works and as far as the way that the Windows API is sort of laid out. So there's going to be a lot of my shitty diagrams and possible analogies and shit like that. But you're going to come away from this, hopefully, with a much deeper understanding of how the hardware and the APIs and the frameworks and what and the hoo-ha and the whatnot, how it all works together. And that will enable you to understand the code that we use to interface with those systems. So, next lesson, I'm not sure, I'll probably break it up. I'm probably going to break the framework explanation up into 2 or possibly 3 lessons. So, but the next lesson should be a lot of background on how DirectX and Windows and graphics hardware all work. And yeah, maybe we'll get into some going over the actual code, or maybe that will be the next one. I haven't decided how I'm going to work all that shit out. But the basic, in my mind right now, the basic idea is maybe a quick overview of the framework, going through all the different source files and just generally explaining what they handle. Then I'm going to go into depth about the graphics hardware, and then about the DirectX and driver system. And then I'm going to go into depth about talking about how Windows API programs work. And after you've learned how the systems work, then I will go through the source files and explain in depth what everything is doing. And finally, we're going to start with a totally blank project, and we're going to rebuild the framework from scratch. That's my plan. So by the end of this, that'll force us to basically figure out what everything does and make sure I don't miss anything when I'm explaining what every part of the framework does. And at the end, you will be able to make your own, well, I wouldn't call it a framework, but you'll be able to make your own DirectX applications from scratch. So yeah, in case you were, planning on making like a commercial game or something, then you'll be able to do that without having to make it open source, which would kind of be a bummer if it had to be open source, right? So yeah, at the end of this next sequence of 2 or 3 lessons, you will be able to make your own direct 3D application without relying on the framework. Of course, we'll still be using the framework for lessons after that because it's convenient, but nevertheless, you will be able to make stuff without it if you so desire. So look forward to that. And yeah, that's it. Chili signing out.